This is the third problem in the sheet that says uniform circular motion, examples, and practice problems. A car is driving over a semicircular shaped hill. The hill has a radius of 4 meters. What is the fastest speed that the car can have at the top of the hill and not fly off? So what's going on here? You've got a hill. You've got the car going around the top of the hill and it's moving. And we want to know how fast this car can go without actually leaving the hill. The only two things we're given is that the only one thing we're given is that the radius of the car is, that the radius of the hill is equal to 4 meters. And what it's asking for is the fastest speed that it can go without flying off the hill. So we're looking for a speed. If the car leaves the hill, the only force acting on it would be the force of gravity. So in other words, it's going to go fast enough so that it just barely leaves the hill, but we want to solve this as if it has already left the hill. The reason we're doing that is the fastest speed that it can go around will be the speed that it actually 1.0001 whatever meter per second over that will cause the car to leave the hill. So we're going to solve this as if the only force acting on the car is the weight. Our centripetal force from this force diagram is equal to top minus bottom, so negative Fg. If you recall, anytime you're at the top of the hill, you have to make sure that the centripetal force is negative. In this case, it cancels out, so your centripetal force is just equal to the weight. We know that centripetal force is equal to mv squared over the radius, and we know that the weight is equal to mg. You don't need mass because right here, mass goes away. So v squared over r is equal to g. V squared equals rg. So the maximum speed is equal to the square root of rg. V equals the square root of 4 meters times 9.8 meters per second squared. And this equals 6.26, keeps on going, meters per second. So the maximum speed that this car can go over the hill and not fly off with 1 sig fig is about 6 meters per second. Anytime you see a problem like this where it's asking for fastest speed or maximum radius or anything where it's saying for an object to just stay on a surface and not fly off of it, you're going to solve the problem as if the only force acting on it is gravity. Again, we do that because as soon as it would leave the hill, this would be the only force acting on it. And any minuscule amount of meters per second over this number is what would cause this to happen. So we solve the problem this way in order to figure out what the maximum would be. I'm going to do the next problem as well. So right underneath this where it's talking about the coefficient of friction, and then we'll be able to apply these to some more practice. The coefficient of friction between a 1,500 kilogram car and the road is 0.3. How fast can the car travel around a curve of radius 50 meters if friction is the only force keeping it in the curve? Okay, so we've got our car. It's driving around some kind of curve. Oops. Again, hard to draw these on angles. And essentially what we want to do is make sure that this car is not going off the road. So friction is the force keeping this car in the curve, making sure that it doesn't go flying off. What are we given? We know that the mass of the car is 1,500 kilograms. Tells us that the coefficient of friction, remember mu? Mu equals 0.3. And the radius of the curve is 50 meters. And just like the last problem, this one again is asking us for a speed. So we want to know how fast the car has to go, not necessarily the maximum, but how fast, what is that perfect speed the car needs to go to make sure that it stays in with the curve. Okay, so if we draw a force diagram for the car, and let's just say that center is somewhere over here. So this is the center of the curve. So center somewhere over here. You're going to have a weight and a normal force for the car. And this is hard to draw kind of two-dimensionally. So you have a weight and a normal force for the car. It's going around a circle. So let's say this is the circle that the car is going around. And center is this way. So the frictional force is directed towards the center of the circle. Looking from this force diagram, my centripetal force is equal to right minus left, so a negative frictional force. Just like when you're at the top of a circle, if you're towards the right of a circle, then your centripetal force also has to be negative because center will be left. So these both cancel out to be positive. So my centripetal force is my net force. The only force acting in the direction of the center of the circle is friction. So that's why this is true. mv squared over r is equal to my frictional force. If you recall from before break, frictional force is equal to mu Fn. And looking at this particular force diagram, Fn equals Fg. So frictional force equals mu Fg. We also know that Fg equals mg. So frictional force equals mu mg. I'm just going to put this in for frictional force over here. So mv squared over r equals mu mg. Again, we were given a mass, but we don't need to use it. And you'll see that pop up a lot, especially if you start breaking things down, as I did just right here. So v squared over r equals mu g. V squared equals mu g r. We were given mu, we were given r, and g is a constant. I'm going to go to the next thing out of room. So v squared equals 0.3 times 9.8 meters per second squared times 50 meters. This number comes out to an even 147 meters squared per second squared. For v squared, now we have to take the square root of both sides. So the speed to stay in this curve equals 12.12, keeps on going, meters per second. Only one sig fig, so v is about equal to 10 meters per second. Similar to the previous problem in that you ended up not needing mass, and that's actually simplified to something really easy, v squared equals mu gr. Not needing mass, the only thing you needed to know in this case was the radius and the coefficient of friction. The difference between this problem and the last problem was that friction. In the last problem, all you needed to know for maximum speed was the radius. So you'll see other problems similar to these, just be careful in what it's asking for. But know that if it looks like you're not given enough information, you most likely have exactly everything you would need, as long as you break everything down into their simplest equations.